Okay, I think we can start. So welcome back to the seminar on 3D geometry and vision. Today we have the pleasure to have Michael Bronstein speak, as well as guest panelists Gerard Ponsmo and Max Osvianikov. Michael Bronstein is a professor at the Imperial College London. Previously, he was also a professor at USI Lugano and received his PhD with distinction from Technion. So Michael Bronstein does a lot of fundamental research in theoretical and computational geometry, with applications ranging from machine learning to computer vision and computer graphics. He's an extremely prolific researcher with also many awards, ERC awards, Google Faculty Research Awards, and as well as many publications and books. So he's not only doing a lot of really cool stuff in geometry understanding, he's also got a couple of startups that were successfully acquired, like Envision and Fabula AI, and is also head of graph learning research at Twitter. So today he's gonna speak to us about geometric deep learning for 3D shape analysis and synthesis.
Thank you very much. So really great pleasure to be here. So I guess I will try not to repeat myself because I've been giving many talks about deep learning on graphs. So today I will try to present it more from the perspective of computer graphics and computer vision. So before we dive into what we call geometric deep learning, let me take a couple of steps back and talk about an important concept in machine learning in general, which is called the inductive bias. Essentially, it's the set of assumptions that we need to make about the problem and the data, and that goes into a machine learning algorithm. And if we take a very simple machine learning system, such as multi-layer perceptron, we know that these kind of neural networks are universal approximations. Basically, they can approximate a continuous function to any desired degree of accuracy. So it seems like a good piece of news, right? We can represent anything, so they are very expressive. But actually, when we try to apply these kind of simple neural networks to real high-dimensional data, they tend to fail miserably. And this is very well demonstrated in computer vision problems such as digit classification. So if you take this image and stack it into a vector and pass it to a neural network, and then there is a shifted version of the same digit, then the input will be very different, and the neural network will really struggle to learn that this is the same digit. So it doesn't have any structure of the geometric structure of the image. So it has to learn this simple invariance from the data. It will take a lot of parameters and sophisticated architecture to do it. So you can even find theoretical bounds that come from geometric considerations of high-dimensional metric balls, basically how many examples you need to approximate such functions. So really the breakthrough in computer vision happened from abandoning this generality and incorporating some problem-specific invariants. And the success story of convolutional neural networks was exactly this. Basically, convolutional neural networks, as we'll talk more in details in the following few minutes, incorporate what is called translation invariance, or more correctly said, translation equivariance, by sharing the local weights. So this is hardwired into the architecture, and this way drastically reduces the number of parameters and allows to make these neural networks work on high-dimensional image data. So let me show you another type of problem. So in this case, it's a molecule represented as a graph. So we have atoms represented as nodes and chemical bonds represented as edges. Let's say we want to predict some property, let's say atomization energy of this molecule. By the way, this is a molecule of caffeine that probably many of us like very much. The problem here, compared to the previous example of images, that we can permute the nodes in any way we want, right? So there is usually no canonical way of ordering the nodes of the graph. And these kind of structures, graph structure data, appears prominently in many problems, for example, in social networks or in biological interaction networks, and also in computer graphics and vision, where we use, for example, meshes to represent three-dimensional objects. So these are graphs with some more structure, and I will talk in more details about what are these extra assumptions and extra structures that we have in meshes compared to general graphs. And in 2016, I co-authored a paper with Johan Brune, Jan Lecan, Arthur Schlam, and Pierre van der Geinst, where we tried to connect several disparate research topics that were around that time, basically trying to come up with right inductive biases for non-Euclidean structured data, what we called geometric deep learning. So geometric deep learning really encompasses two prototypical objects, manifolds and graphs. If I have time towards the end, I will try to extend it to a little bit more than that. And apparently these are very different structures, right? So even if you ask people that work on manifolds, differential geometers, and people working on graphs, basically graph theorists, they even not sit in the same on the same floor in the math department. They maybe quietly hate each other. They don't go to the same conferences. So these are completely different fields of mathematics, and yet, at least from some perspectives, they're very similar. And I will try to show the similarities and differences between these very different objects. So geometric deep learning is essentially, the juice of it is about finding the right inductive bias for this kind of non-Euclidean structured objects, for graphs or for manifolds. And this is exactly the kind of generalizations that I would like to talk about today. So the history of geometric deep learning is pretty old. At least we can trace back some works on deep learning on, maybe it was not called deep learning at that time, but at least neural networks for graph structured data, probably since mid-90s. But I think it would be fair to say that the bulk and the more interesting applications and let's say the more working and practical architectures are probably from the past 5 years. And today I will be focusing mainly on 3D graphics and vision problems. So I will obviously present a rather egocentric picture, mainly talking about our works, but I will mention many other works that have been done in the graph learning community that are very much related to what we do in computer vision and graphics. So this is also one of the hottest topics in machine learning currently, at least judging by the submission statistics in these years are clear. So graph neural networks, one instance of geometric deep learning, is extremely prominent, has grown vastly over the last couple of years. And you really find a lot of applications where graph neural networks and geometric deep learning have been used, from recommender systems to fake news detection to drug repositioning and computational chemistry. And if we look at computer vision, I would say that there has been a tectonic shift that has happened in the past. Well, one of them, of course, was due to the adoption of deep learning methods, but another one is that probably 20 to 15 years ago, people in computer vision tend to dismiss 3D data. And I remember myself still as a student trying to publish in vision conferences. People were saying, oh, you're working on 3D data, so you're in computer graphics or geometry processing. And I tended to show this kind of picture. This is probably from 15 years ago, one of my old presentations, showing that, look, actually, the two fields are really related. But fast forward nowadays, so this is from this year's CVPR, really the main topic, prominently also prominent from the best paper nominations and awards, is that nowadays, or at least this year, CVPR was really about geometry plus deep learning. So the two best paper awards were about geometry and deep learning, and so many of the nominated papers. So it's interesting to see, maybe ironically, how the field has changed. Now, one of the reasons why this happened is also due to the simplicity and availability of three-dimensional data. So if 15 years ago, it was very difficult to get high quality 3D data and structure from motion, let's say the typical kind of sources of geometric data in computer vision were very poor quality. Nowadays, you have 3D sensors that you can basically, that are embedded into your iPhone, right? So that was already 3 years old technology. And I myself was involved, as Angela mentioned, in a company called Envision that was acquired by Intel, and this is now known as Intel RealSense. So this is mobile sensors that you can find ubiquitously nowadays on the market. So I like showing this illustration. So this is from FaceShift. So that was the company that was acquired by Apple from the group of Mark Pauli and others. And basically, this is markerless motion capture. This is what the technology that powers the Animoji of Apple iPhone. And basically, behind the scenes, you can find two prototypical problems in computer vision and graphics. And these are shape analysis and synthesis. So you have the real-time capture, the scan of the face that is noisy and partial. You first correspond it to some canonical facial template, and then you deform, you reanimate this template, synthesize a new object that repeats the input facial expressions. And here we have two problems, the problem of analysis, such as the problem of correspondence, and the problem of synthesis. And I would like to talk today about how to address both of these problems using geometric deep learning. Now, what is geometric deep learning in this context? We are trying to basically to find in the analysis problem deformable correspondence. We want to find correspondence between points on the surfaces that are invariant to deformations of the input. And here really the choice of representation is key, because it can make your problem very difficult or rather simple. And of course, when we think of, let's say, face or 3D object in general, there are many ways to think of it. We can think of it as a collection of images, so multi-view methods such as multi-view CNNs can be applied in this case. We can think of volumetric representations. Some early works date back to the 2015 probably, and there are many other works. Well, the hosts of this seminar are prominent researchers in this field, so Angela and Matthias Niesner have worked and have done a lot of work in this domain. And if you think of medical image analysis, it's very natural to think of volumetric data. Then we have point clouds, and this is also something that is quite popular because this is a natural format of data that comes from, for example, LiDAR. So if you think of self-driving cars, you like to want to work with point clouds, and they're basically the learning problems are learning on sets, architecture such as PointNet. So meshes are somehow objects that we like in geometry processing and in computer graphics, but they're a little bit esoteric for computer vision. So there is this gap that one of the reasons why people in computer vision didn't like meshes, because they're somehow nice and high quality and usually come from CAD programs rather than acquired. So why meshes are good for these kind of problems? Because what I will show you today is you can, if you design the right architecture, basically intrinsic analogy of convolutions, you get an architecture that is by construction invariant to deformations. And probably this picture illustrates it in the best way. So in traditional convolutional neural network, if you apply a filter on, let's say, a 2D view of the image, you see that the result of the filter will be very different if the shape deforms, let alone deformation. Even rotations are not addressed by convolutional neural networks. On the other hand, if you design this filter on the surface itself, as I will explain in today's talk, we get automatically this deformation invariance. Now, the basic building block, of course, here is convolution. And in images, we're very familiar with convolution. We can think of it as a kind of template matching or sliding window. What is the analogy of convolution on non-Euclidean structured data? And one of the things to understand is that we don't really have a vector space. So we cannot think of it as a kind of sliding window. So we need to revisit the very basic formulation. One thing that, for example, we will discover is that unlike the Euclidean setting where we can think of a pixel and it's a very democratic setup where the pixel always have the same number of neighbors that are presented in the same order, in graphs or meshes, we don't have this luxury. So we have some ambiguities. And therefore, the properties of such architectures will be very different. So the main questions that come with this new definition is how to define convolution-like operations on meshes and on graphs, how to do pooling. So for the sake of time, I will skip the pooling. I will focus mainly on convolution, and how to do it efficiently. So these will be the main topics that I would like to discuss today. So let me take another step back and remind you, or maybe to present slightly differently, what is convolution, a concept that everybody is familiar with. Okay, so Euclidean convolution essentially looks like this. So we have some grid, one-dimensional grid. We have a signal defined on this grid. And what we do, we somehow aggregate linearly some neighbors of a node, right? So this is exactly what is meant by shared weights. So if we write the matrix of weights of a convolutional neural network, it has this diagonal structure where the parameters are shared. So the elements on these diagonals are constant. So we can write the output of convolution as this matrix vector product, where we need to basically take a vector of coefficients, and we also need to take into account the boundary conditions. So it's convenient for me to think of periodic boundary conditions. So essentially, it's a signal defined on a circle. And we shift by one position each time this vector. And this produces what is called a circulant matrix. So the two notions are equivalent. You can think of convolutions as circulant matrices. Now, unlike general matrix multiplication, circulant matrices are very special. They are commutative. And one choice of circulant matrices is the shift operator. So convolution as a result commutes with shift. This is a property that we call shift-equivariance. Sometimes you will see it under the name of shift-invariance, but the correct term is equivariance. So the commutativity means that I can first apply shift and then convolution, or vice versa, the result is the same. Now, another thing that we know about commuting matrices is that they are jointly diagonalizable. So in this case, it means that we will have the same eigenvectors, and it's enough to pick up one matrix and study its eigenvectors. And it's convenient to look at the eigenvectors of shift, which happen to be the Fourier basis. And therefore, convolutions are diagonalized by the Fourier basis or by the Fourier transform. And the last bit of this picture is that actually the eigenvalues of a convolution or a circulant matrix are given by the Fourier transform of the coefficients of the vector that forms it, this vector W. And this gives us what is called in signal processing the convolution theorem, establishing a duality between spatial domain and frequency domain. So we can apply convolution in the spatial domain by multiplying by a circulant matrix or doing this sliding window operation, or we can do it in the frequency domain by applying the Fourier transform, element-wise product, and then the inverse Fourier transform, right? And this is how signal processing or filtering is done in signal processing. You design the filter in the frequency domain and then apply it to the Fourier transform. So let's recap for a second. Basically, in the spatial domain, convolution is a circulant matrix. You can think of it as local aggregation with shared parameters. And this spatial structure comes from the underlying grid. We also know that circulant matrices are diagonalized by the DFT, which are eigenvectors of the shift operator. And therefore, we have the dual formulation of convolution in the frequency domain, right? And you can do convolution either in the spatial domain with order of n complexity, if the filter is small, order of 1, or you can do it in the frequency domain using fast Fourier transform in n log n complexity, which is, for any practical consideration, is almost as good as order of n. So how do we do non-Euclidean convolution? And here again, we can make this analogy and do it either in spatial domain, so some kind of local aggregation on adjacent nodes, which we will now need to define, or in the frequency domain by generalizing the Fourier transform. As we'll see further down the road, the two views will be equivalent, but let me start with the spectral perspective by generalizing the Fourier transform. So one thing to understand about grids is that the shift operator is the adjacency matrix of the grid, of the ring graph that models the grid, right? So you can see that this is the adjacency matrix of this graph. And as a result, we can look at eigenvectors of the adjacency matrix or any other circulant matrix for this purpose. For example, the Laplacian operator, right? They all commute, so they all have the same eigenvectors. Now, what is good about Laplacian that it can be defined on a lot of structures. So on the grid, for example, it is a kind of local averaging. So it tells, the Laplacian operator tells you the difference between your surrounding and the point itself. And that's why Laplacian is so common in the equations of mathematical physics, such as the heat equation, where it is a differential version of what is called in physics the Newton's law of cooling, right? So Newton's law of cooling tells you that the rate of change of temperature is proportional to the difference between the temperature of the object and its surrounding. So the rate of change is encoded by the temporal derivative, and the difference between the temperature and the surrounding locally is encoded by the Laplacian operator. You can define Laplacian on graphs. You can define Laplacian on manifolds. This is called the Laplace-Beltrami operator. And on the discretization of manifolds, which are meshes, there are many ways of discretizing the Laplacian. One of the most popular ones is the cotangent formula that is ubiquitously used in graphics and geometry processing. Now, the key idea of generalizing the Fourier transform is to use the eigenvectors of the Laplacian as the analogy of the Fourier transform. And for undirected graphs where the adjacency matrix or the Laplacian are symmetric, these matrix has orthogonal eigenvectors. For meshes, if you use the right discretization of the Laplace-Beltrami operator, this is also the case. And I said Laplacians can be defined on diverse structures. So you can really define anything you want and define a Laplacian with, for example, it can be even a metric space. The constructions of Laplacians are even on such abstract notions. So the good thing about their Fourier formulation is that once you have constructed your Laplacian and you computed its basis, basically you can forget about the underlying discretization and work only with representation with respect to these bases. Now, in the classical case, the Fourier basis, the traditional Fourier basis, the sines or cosines are the eigenvectors of the ring graph Laplacian, right? And we can think of eigenvalues as frequencies and the eigenvectors as the basis functions. So the same analogy holds for non-Euclidean structures. So here you can see the first eigenvectors of Laplacian of a graph and a mesh representing a human body in this case. So here the red values represent positive numbers, and blue value represent negative numbers. Now, how do we do convolution in the spectral domain? Exactly as we did before, we just replace the Fourier transform with this generalized orthogonal basis of the Laplacian. So to compute convolution of x with w, we first apply the Fourier transform, multiplying by phi transpose, right? Projecting on the basis of the Laplacian eigenvectors. We then apply the filter, multiplying by a diagonal matrix of weights, and then we compute the inverse Fourier transform, multiplying by phi. Okay, so far it looks exactly the same as before. Now here come the bad news. First of all, the computation of Fourier transform now costs us order of n squared because it's product by a dense matrix, and we usually don't have fast Fourier transform on graphs or on manifolds. Now this is just multiplication, computing the eigenvectors, basically diagonalizing the Laplacian. In the worst case will be order of n cube. Then, of course, the computation of the filter is linear, and then the inverse Fourier transform has the same complexity. So if we compare this to the classical case, we had n log n, worst case complexity order of n. So this is significantly worse. Second thing is that now the number of parameters is dependent linearly on the input size. And before, one of the cool things about convolutional neural networks that actually we can apply them on gigantic images. The number of parameters is the same. So this is what made the big difference compared to, let's say, standard neural networks, where the number of parameters is dependent on the input size. So this is also not good. We also have some nasty things like no guarantee of spatial localization because the filters are designed in the spectral domain, and the filters are isotropic, so there is no notion of direction. And probably the worst, that the filters are basis dependent, so they don't generalize across domains. And let me visualize this later problem. So here we have a manifold. We have some function defined on it. I design a filter that does a kind of edge detection in the frequency domain. So I compute the Fourier transform, basically multiplying by the eigenvectors of the Laplacian of this horse, multiply then by the diagonal matrix of weights, and then compute the inverse Fourier transform. Now, when I even slightly deform this horse, what will happen? The Laplacian will change, the eigenvectors will change, the coefficients are kept the same, but the result of the filter will be completely different, right? So in general, especially high frequencies are extremely unstable under perturbations. And this is not surprising. We know that coefficients do not really speak in the same language. So the basis across different shapes are different. And here we are talking about near isometric deformations. So the second problem I mentioned is that filters are isotropic. So as a sanity check, if you compute these kind of Laplacian filters on a grid, you see that they look like concentric circles. And this is also not surprising because, as I said in the beginning, on grids we have a fixed order of neighbors. So we can always talk about a neighbor to the left or a neighbor to the right. on graphs, on the other hand, we can shuffle in arbitrary order the neighbors, and the result will be the same. Basically, there is some local permutation ambiguity. We don't have immediate notion of directions on graphs. And for example, if you do compute the Laplacian averages the neighbors, and this is a permutation invariant operation. So as a result, isotropic filters are obtained from this spectral construction. I should say that on meshes we have more structure, so meshes are locally Euclidean, and here we do have ambiguity of how to choose one of the vertices, but once we fix it, we can order all the rest of the vertices in one ring in certain way. For example, we can order them using clockwise orientation. So instead of permutation ambiguity, we have rotation ambiguity, and this is significantly more structure. As a result, for example, we can do anisotropic filters. I will talk about it later. So to address the problems that I highlighted before, the lack of generalization and the number of parameters, let's think of convolution somewhat differently. So we can think of it as a matrix function that is applied to the Laplacian operator, and we interpret it as basically a spectral transfer function. It's applied to the operator in the operator sense. Basically, it's a function that is applied to the eigenvalues of the operator, which we interpret as frequencies. And if we make this function parametric with fixed number of parameters, then we got rid of this necessity to have number of parameters dependent on the input size. If we can express this function in terms of simple matrix operations, such as matrix vector products or powers, we can altogether avoid the explicit computation of the eigenvectors and make this convolution efficient. And we can also show that we can guarantee stability, so basically generalization, something that we didn't have with explicit computation of the basis. And we can also guarantee localization or even compact support. So I refer to the papers that we wrote together with Ron Levy a couple of years ago. So the simplest choice of this filter is a polynomial, where we have the number of parameters equal to the degree of the polynomial plus 1. And it's efficiently computed by just taking the powers of the Laplacian, and because usually we're dealing with sparse matrices, it has a complexity that is order of the number of edges, which is roughly the number of nodes in the graph or the mesh. So we don't need to diagonalize the Laplacian anymore explicitly. The filters are also localized because Laplacian is a local operator, so its p power is localized to p hops. And we can show generalization across graphs. We can apply it to operators that are not necessarily symmetric, because we don't need to explicitly assume that it is symmetric matrix with orthogonal eigenvectors. And we can use it to other matrices, not necessarily Laplacians. So in graph neural networks, it is common to use some form of adjacency matrix instead. So one of the problems when you apply these kind of filters to meshes is the dependence on the mesh density. So here you can see that the, for example, 2-hop region on a dense mesh or a sparse mesh will be very different. And therefore, nobody really uses polynomial filters in computer graphics and geometry processing. It's better to use rational functions. And we also had a work with Ron Levy where we showed how to do rational filters in the context of geometric deep learning, primarily for graphs, but this can be applied for meshes as well. Now, a question that is that you might ask is actually how powerful are such filters? And this is an important topic in geometric deep learning in general. So there have been some results on expressive power of graph neural networks that relate graph neural networks to graph isomorphism tests. So with Yu Wang, a student of Justin Solomon, we did the work that studied it for meshes. And basically the idea is to think of a mesh from the operator view. So if you think of a mesh with some coordinates x and some triangulation t, you can encode this structure in the form of an operator, let's say Laplacian operator, but it can be other operator as well. And from such operators, you can recover up to some degrees of freedom the original mesh. Now, what we want to obtain here in the kind of invariance that is meaningful in computer graphics applications is remeshing invariance. So if I have another mesh that represents the same object with a different operator A wave, I want that the quantities that I extract, that I learn from these two meshes, will be the same. So if we assume that the two meshes are related by means of a functional map, and we assume that this map is area preserving, meaning that its representation is orthogonal, basically the descriptor that we are trying to learn with geometric deep learning architecture must satisfy this property. And you showed that in this case, what essentially we learn is a function of the eigenvalues of this operator. So no matter what you try to do, if you assume this maybe a little bit restrictive setting of remeshing invariance under some technical constraints, basically you learn a very boring stuff. You learn a function that is just a filter of the eigenvalues of the frequencies of the operator. Now, the thing that you need to understand here, that the choice of the operator is up to you. And what we can do is to construct more interesting learnable operators. Okay, so this brings me to this analogy and the link between spatial and spectral view on the convolution. And so let's take the step back again, and let's look at the Euclidean case. So we've seen that convolution looks like this circulant matrix. Now we can think of circulant matrix as a combination of shifted versions of basically the adjacency matrix, or the power of the adjacency matrix, or the power of the shift operator, which are exactly the same for the grid, and we just combine them with different weights, right? So that's exactly how convolution looks like in the Euclidean case, and this is why we get isotropic filters, right? So basically, the equivalent of adjacency matrix on meshes or on graphs will be these p-ring neighborhoods. Now, on meshes, we have more structure, so we can do better. We can do anisotropic filters. And for example, we had a work with my former PhD student, Davide Boscaini, where we constructed an isotropic version of Laplacians using some tangent vector field that will guide the diffusion. And we can do diffusion that spreads faster in certain directions, which again are defined locally on the manifold. And this is opposed to isotropic diffusion that we get in the original setting. Now, one different way of thinking of it is a kind of local system of coordinates, where we, for example, we can construct a polar geodesic system of coordinates around each point, and we can create a system of weights, basically some kind of kernels around these in the system of coordinates. And one way of thinking of it is a kind of patch of pixels, where these weights act as soft pixels, and they solve one of the problems that the number of points in the neighborhood of a vertex on a mesh might be very different depending on the density and the geometry or the topology of the mesh. So you can think of these weights as pixels, and then you can apply standard convolution in this representation. So we call this the page operator. It comes with this caveat that we don't really have a canonical way of orienting these patches. So in the first work that we did on geometric deep learning on meshes, we proposed a mechanism that we called angular max pooling. Essentially, it's a template matching with rotating template. And this was the first architecture, to my knowledge, to apply the analogy or generalized convolutional neural networks to meshes. I would say that in retrospective, it was probably somewhat naive and poorly designed architecture, and it has been obviously superseded by some modern works, including from ourselves. So if we look at it in a very abstract way, essentially, after you do all these kind of local system of coordinates and weights, essentially what you end up with is a large fixed matrix that is independent on your data. So you can think of it as diffusing your features that live on the nodes of the mesh or the graph with some fixed matrix that might be parametric, like in polynomial filters we've seen, but importantly, it's independent on X. And if you think of it, this is the blueprint of many popular architectures, including in graph neural networks such as GCN, ChebNet, ChebNet, and so on and so forth. Now, we can make it slightly more interesting. We can make it still linear, so it's a linear combination of the node features, but now this combination, the weights themselves, depend on the node features themselves. And in graph neural networks, a popular architecture of this kind is graph attention, which can be seen as a particular setting of our architecture that we developed together with my PhD student Federico Monti back in 2017. And this is called the Monet architecture. And essentially, you can think of it as a generalization of the previous geodesic CNN architecture, where we also allow to learn the page operator. Basically, we optimize for the parameters of these weighting functions. So if you look at the way that these blobs look like, so for GCNNs, for example, they have some fixed pattern. For anisotropic diffusion, they have another fixed pattern. For Monet, they are optimized during the training, and you get some optimal positions and shapes of these blobs that are optimized for the downstream task. And the last most general way of considering these kind of convolution-like operations are nonlinear feature-dependent operators. And this is how message passing graph neural networks look like, or how what we call edge convolution looks like. So this is the work that I did with Yu Wang and Justin Solomon and a bunch of other people at MIT. Basically, here we can think of a general edge feature function that takes pairs of nodes, basically a node and an adjacent node, possibly also features of the edge if there are such. And they're aggregated with some general aggregation operator, can be a maximum, sum, or whatever. And then edge convolution is just aggregation of these feature function outputs in a neighborhood. So what is good is that it doesn't need to be applied on meshes. Actually, it can be applied on point clouds, where the graph is constructed on the fly as the k-nearest neighbor graph. And this is a way of going beyond a simple shared function that you apply on a set, like in point net architecture. The graph in this case represents the local structure of the data. That can be a geometric structure of the input, but it actually can be updated between the layers of the network. And we show in this example of shape point cloud segmentation why it makes sense that initially you start with geometric notion similarity. So here the colors represent proximity from the red point, but as you go deeper into the network, it becomes less and less geometric and more semantic. For example, in the third layer, it groups together the two engines of the aircraft, or the two wings, and so on. And these ideas actually are connected to some older methods in machine learning called manifold learning or nonlinear dimensionality reduction. So I've recently written a blog post on this on Medium. You're welcome to have a look. I'm trying to connect some of these approaches. And at that time, it was state-of-the-art model on point cloud classification and segmentation, probably now superseded by some modern architectures. I think ironically also, it took more than 2 years to publish it in SIGGRAPH. So by the time it was presented this year, it was probably already obsolete. But it's quite popular architecture, and it's especially popular among theoretical physicists that try to use it for high energy particle physics experiments. So let me talk about more applications in shape analysis. And again, I will give this illustration of the two canonical problems in shape analysis and synthesis. And we start with the problem of shape analysis, so the problem of deformable shape correspondence, right? And we said that basically all the main motivation for us to construct these weird filters on the shape itself were to get invariance to isometric deformations. And if you apply these kind of architectures to the problem of shape correspondence, basically it's a point-wise classification problem. You choose a canonical shape as your label space, and you try to label each point on the input shape with the class of that corresponding point. You get actually very accurate correspondence. So these are results of correspondence we obtained with Monet. This is again 3 years old result. Now we can get better. You see that the overall texture mapping is very good. So there are almost no distortions. It is also good to visualize it as a local correspondence error, basically deviation from the ground truth. And just for comparison, this is blended intrinsic maps, well, classical work by Kim and Lippmann and Funkhauser. You see pretty significant distortions. This was the geodesic CNN, our first work on intrinsic convolutional neural networks. Better results, but you have a few spots where the error is large. And this is what we obtained with MONET. So at that time, this was really remarkable quality of correspondence, and testing it the usual way on Princeton benchmark, basically plotting the fraction of correspondences falling within certain error radius, we see that we got basically above 95% accuracy, with maximum distortion being of the order of 4 centimeters for human shapes, which is very small. And then we can even improve it, and we show that we could saturate this benchmark by using regularization that is based on functional maps. So that was the work we did with Orolitani, called FMNet, and there was recent work from the group of Max Ovsyanikov that basically improved a similar idea, obtaining even better results for functional map-based correspondence with deep learning. Now, let me take a little bit of a detour and talk about a somewhat exotic problem in computer graphics and vision. Nevertheless, it is very geometric, and I'm very excited about it because I believe this will be one of the fields where potentially geometric deep learning can make a big impact that really matters to literally to the life of all of us. And this is the domain of protein science and more broadly drug design and development. And we're talking about proteins. So I don't know how much you know about proteins. Well, when I started working on these problems, I knew roughly about proteins. Well, it's the kind of stuff that you drink after your exercise in the gym. But literally, proteins are molecules of life. So we don't know any life form that is not based on proteins. And proteins responsible for anything, any important process, biological, biochemical process that comes to your mind, there are proteins involved. Whether it's signaling in the form of hormones, these are proteins. Whether it's transporting oxygen to our cells, this is hemoglobin, another protein. Defense against pathogens, antibodies are also proteins, and so on and so forth. So they're really everywhere, from defending us against diseases to catalyzing reactions by a natural catalyst called the enzymes. So what are proteins? You can think of them as one-dimensional sequences of basic small molecules called amino acids that are stick together in a chain that by virtue of electrostatic forces fold into complex three-dimensional structures. So a good analogy is this snake toy that is one-dimensional, but you can bend and fold it into anything you want. And at least in my childhood, that was really cool. That was really cool thing to play with. Now, proteins, the function of proteins is to bind to each other and to other biomolecules. And a good analogy that actually dates back to Emil Fischer, a Nobel laureate, describing it using the lock and key metaphor. So basically, there is some geometric complementarity between these two structures that makes them bind or stick together. Now, it's not only geometric complementarity, it's also electrostatic complementarity, because these are charged surfaces. Now, same thing as talking about what is the right representation for 3D structures. In protein science, there are many representations that you can adopt. So you can think of them as just clouds of atoms. You can think of them as graphs, what is called stick diagrams. You can represent them. That's the usual thing that you see when you visualize proteins, secondary structures, for example, the helixes or the sheets and so on, and also molecular surfaces. So obviously, I'm now talking about deep learning on meshes or on surfaces. Let me try to convince you why molecular surfaces make sense. So first of all, if you look at the surface, just by observing it, you see some patterns that are indicative of binding. So for example, traditional drugs are designed to fit into some pockets. And usually this is what is called druggable surfaces, when they have some holes into which you can fit a small molecule of a drug. Now, second thing is that this representation allows to abstract out the internal structure. And I think this is cool video that shows a physical model of a protein. You see a lot of complex stuff, these helixes inside, but what matters for binding this small molecule that is fit inside the pocket is just the external surface. What happens inside all this internal stuff is of no meaning at all. And last but not least, proteins are really deformable surfaces. So they wiggle. There are some quantum mechanical phenomena that explain why they move all the time. So when the proteins bind, they really deform. And all these can be addressed to some extent by geometric deep learning. So this is what we did. So this was a work that took almost 3 years to do, and that was most of the credit goes to my collaborators at the PFL from the group of Bruno Correa. They actually designed proteins in wet lab. So we describe proteins using geometric deep learning, using electrostatic and chemical and geometric features, and using the monet architecture to do some task-specific layers. And we can address many problems in protein analysis. One of them is, for example, predicting whether certain parts of the protein will bind to some other molecules, to other proteins. We can do fast docking, basically testing one protein against many candidates. And this is potentially very useful for the design of drugs, especially a new class of drugs that is called biological drugs or biologics. And here one example, real example of application, which was actually recognized by the Nobel Prize 2 years ago. This is how cancer immunotherapy works. So this is what is called the program death ligand complex, or PD-1, PD-L1 proteins. And most of the cancers that exist in our body, actually, we create cancer cells on an everyday basis. Why don't we die from these cancers? Because these cells are detected and killed by our immune system, by the T cells. What happens in some cases that some of these malignant cells express proteins that indicate to the immune system that there are healthy cells. So they evolve these PD-L1 proteins on the outside that deactivate the T cells. So biological drugs work by basically binding some molecule to these one of these receptors and deactivating this mechanism, which allows the immune system to kill naturally the malignant tumor cells. And this is the kind of stuff that we are trying to do. Basically, we have a cancer target. We can predict the binding site for these molecules, and we can detect some seeds that are likely to bind to it, and then build a protein around it, which hopefully will also be administered and metabolized properly in the human body. So this was a method that my first Nature class paper, we were lucky enough to be featured on the cover of the February issue of Nature Methods this year. Now, maybe in a longer perspective, now we're talking about analysis problem. So there are two classical problems in protein science. One of them is protein folding. Basically, this complicated process going from the one-dimensional amino acid sequence to the three-dimensional structure. You can think of protein design as a kind of inverse folding. So we know some property or some structure, or at least part of this structure that needs to bind to its counterpart, and we want to come up with the sequence of amino acids that produces this this structure. And this is a very big open problem. So this is really the big next step that we are trying to do, and we are doing some work in this direction, how to generate proteins. Basically a neural network that will suggest a protein with certain functionality. And this is probably a good segue into the second class of problems that I called the synthesis problems. And let me visualize it on the problem of human shapes and human faces and bodies and so on. So if we look at the problem of shape generation, the problem of shape generation is very different from image generation because we don't have canonical correspondence between the input and output, right? In the image, usually the way that you train this kind of architecture, such as autoencoders, you compare the input to the output. So you minimize what is called the reconstruction loss. And it's very easy to compute the reconstruction loss because you compare the first pixel in the input to the first pixel in the output, and so on and so forth. In shapes, if the shapes are different, you don't have this correspondence. So what we did, was also a work with Orly Tani and Amish Makadia from Google. We developed the first intrinsic mesh variational autoencoders. And here our assumption was that the topology is fixed. So we had an encoder that takes a surface, encodes it into a latent space, and then from this latent space, decodes it into a mesh where we assume that the topology is fixed. So we have exact ordering of the nodes. And in this training, we minimize the difference between the input and the decoded output. Now, once we did this, we discard the encoder and we leave only the decoder. So with the premise that random samples of this latent space will produce plausible human shapes. And we used this architecture for shape completion. So once we get a partial shape input, we try to generate a mesh by optimizing in the latent space that will fit in some sense in the best way the input, the partial input. And the results were pretty decent. Well, doesn't look great, at least by today's standards, but 3 years ago, it was definitely better than anything else, especially for deformable shapes. And here are some results with real scans with Kinect. So, well, probably faces are a complete mess and fingers as well, but overall it's not bad. I should say that I should do shameless advertisement of a work by my postdoc, Luca Cosmo, together with my former postdoc, Emanuele Rodola. They had a modern take on this problem with an architecture they call LIMP, where with some extra regularization and extra structure, they are able to obtain significantly nicer looking results. So the main message here, I think, is that if we have some objects for which we know their class, like human shapes or human faces, we can actually assume that we have a canonical model, canonical mesh, which is fixed. And essentially, the synthesis boils down to some canonical ordering of the nodes of this mesh. So one meaningful way of doing it is, for example, using spiral scans of the vertices around the node. So this idea comes from the work of Isaac Lim from the group of Leif Kobelt, and we adopted this sampling strategy for what we call SpiralNet. So that was the work of my PhD student Yorgos Bouritsas and Sergei Bokniak, who obtained state-of-the-art results for shape generation. So it's an architecture that also does some subsampling and then unpooling and upsampling for the face. I should say that in parallel there has been another architecture or several versions of similar architectures done in the group of Michael Black at Max Planck Institute. And this allows us to do the usual stuff that you can do with latent representation of 3D faces. For example, you can take an expression of a person, subtract the neutral expression, add the new identity, and you get the new person in the expression of the first one. So you can do this kind of shape calculus in the latent space. We can also have mixed architectures when the input and the output are in different modalities. So for example, the input can be a point cloud where the encoder has a different architecture, such as PointNet or CNR, and the decoder is intrinsic mesh generating architecture. We can do something like this for hands. So in this case, the encoder is a two-dimensional CNN and the input is a two-dimensional image, and the output is an accurate mesh reconstructing the pose and the shape of the hand. So this was a line of works together with Stefanos Zefiriou, my colleague at Imperial College, and our joint PhD student, Dominique Coulon, that the most recent work was presented at CPR this year. And you can see that with these architectures, you can really do very accurate reconstruction, state-of-the-art results of hands in the wild. And these are very challenging poses, and hands in general are very challenging objects because they have a lot of degrees of freedom and also a lot of occlusions and self-occlusions. Like in some of these images, you see that many of the fingers are invisible. And it allows actually Dominic together with a UK startup called Real AI, they implemented these algorithms on a mobile device. So this is about 10 times faster than real time on a legacy version of iPhone, basically building an entire three-dimensional avatar with accurate hand tracking. And this can be used for different virtual and augmented reality applications, such as examples shown here. And I should say one challenging part that has not been addressed, we didn't look into it, is working with clothing, simulating clothed humans. I've seen recently a paper that tries to do it also using geometric deep learning, basically simulating how cloth would be mapped or put on a human body by varying the parameters of the body shape. So another maybe even more exotic instance of shape from X or face from X. So if you look at this image, it looks like a rather poor reconstruction on the right. What you see on the right is rather poor reconstruction of what you see on the left. But this is not reconstruction from an image. This is reconstruction from DNA. So this is work from my collaborators, Peter Klaes at the University of Leuven, which heads the facial genomics lab there. So together we are trying to basically to condition some of these generative architectures on genetic information. And well, this is maybe a cool layman application, maybe a little bit sensational, for example, trying to reconstruct the faces of some historical figures of the past, such as some prehistoric people or ancient kings. But probably the more interesting and the more serious applications are, for example, detecting different genetic syndromes that can be manifested in the face. And this map of genotype to phenotype is really the holy grail of genetics. It is rather complex, and trying to invert it might not be possible, but even understanding what kind of structures are genetically driven is a very fundamental problem in this field. So let me wrap up. I guess I'm out of time, so really quick conclusions. If we look at geometric deep learning from the perspective of assumptions or inductive biases, we have these two extremes of volumetric representations, where everything is fixed, we have a three-dimensional grid, versus point clouds that are completely unstructured. So meshes somehow fall in between, and we can think of a graph-based representation such as dynamic graph CNNs somewhere in the middle between meshes and point clouds. So obviously the properties are very different. If, as I said, in volumetric representations, we have a fixed grid with fixed ordering. On point clouds, we have global permutation invariance, right? So on local graphs, you have local permutation invariance, and on meshes, you have rotation ambiguity. And the kind of architectures that implement these inductive biases, as what I've shown, for example, geodesic CNNs, Monet, and dynamic graph CNNs. I should say that if we again look at the problem of geometric deep learning, you can think of it as what we call 4G, and this is basically we are trying to make this a little bit broader generalization of what is actually meant by geometric deep learning, together with Bruna, Velichkovic, and Taco Cohen. The 4Gs are grids, groups, graphs, and gauges. Or gauges is maybe a high energy physics term that is equivalent for manifolds. If you think of the Erlangen program, the fundamental contribution of Felix Klein that basically brought algebraization of geometry and unified disparate geometries such as hyperbolic geometry or projective geometry or Euclidean geometry, by looking at invariance, we can also apply the same principles to deep learning. So on grids, these will be certain types of invariance, such as shift invariance, that leads to weight sharing that we see in CNNs. You can generalize it to groups, basically with rotation equivariance, CNNs, and so on. On graphs, this is yet another kind of invariance, permutation invariance, and on manifolds, this will be yet another invariance that we've seen today. So if you take home messages, maybe a little bit arrogant title for this slide. So I think geometric deep learning is really about inductive bias and the architectures that come from it for non-Euclidean data, whether it's graphs or manifolds or the other Gs. And we can think of it also as learnable local operators that are similar to convolution, or they boil down to convolution when you go back to Euclidean settings. There are many applications in vision, in graphics, and beyond. There are some state-of-the-art results, several success stories. Well, Angela mentioned the startup that we sold last year to Twitter, Fabul AI, that I co-founded with my students, Federico Monti, one of them, who was the co-founder and CTO of this company. Basically, this is probably the first commercial success of deep learning on graphs. We're doing fake news detection with graph neural networks. And there are some first industrial applications. Well, we're Twitter is trying to use graph learning algorithms for some problems related to social networks, and there are many other applications as well. It is overall very hot field in machine learning nowadays. A few open questions, just not to leave it with some statements. I think there are many things that we currently don't know. One of them I mentioned, generative models for meshes and graphs, especially with arbitrary topology. Using higher order structures, especially for graphs going beyond nodes and edges, something that is quite clear and very well understood and very common in meshes, for example, that have node, edge-wise and face-wise structures, and the different relations between them, for example, in the form of Hodge decompositions. Analogies of these exist on graphs, but they are unknown and unused in deep learning, in geometric deep learning. So interesting links to computational topology, to simplicial complexes and persistent homologies, for example. And this is related also to incorporating some global structures if we have some constraints about topology, for example, having closed meshes and so on. Working across representations, so sometimes we have different inputs, such as, for example, point clouds or maybe images, and basically representing the same structure and reconciling architectures that might be more convenient to have certain invariants or certain conservation properties, but less convenient to work with as the native representation of the data. And many interesting problems related to expressive power, robustness, and performance guarantees. And finally, as always it happens, you might have a nice mathematical concept that when you come to implement it, you need to round the corners and make trade-offs. So basically a more rigorous understanding of these trade-offs between what works in practice and what you can analyze in theory is, as always, very important. So finally, I should mention the series of blog posts that I'm writing primarily on deep learning on graphs in towards data science. And last but not least, I would like to give credit to multiple wonderful, amazing collaborators I've had the privilege to work with in the past years. And thank you very much.
Thanks, Michael, for the wonderful talk, covering a lot of information across a lot of different fields. So I think we already have a couple of questions here on YouTube. And so anybody who's watching from YouTube, feel free to ask any other questions in the chat. So I will steal the first question for myself. So I'm curious, basically, often in terms of just geometric meshes, maybe not so much for protein modeling and these kinds of things, we find that like with ShapeNet meshes, there will be the same object or the same kind of surface represented with a pretty different mesh connectivity. And so how robust are these approaches to this kind of various different kinds of triangulations for the same surface, and not just different resolutions, but just different meshing? And do we need to change something fundamental to adapt to this kind of problem, especially in the generative case, I guess?
Yeah, well, excellent question. So let me start maybe first with analysis and then talk about synthesis. So in terms of analysis, basically, if you do everything correctly, then the representation doesn't really matter as long as you're representing the same object. So if you have different meshes, for example, you design these local operators properly, then they are pretty robust to triangulations. You can actually argue, for example, if you have sufficiently dense point clouds, does it contain enough information about the underlying object? And probably it does. So in many cases, we see that learning on point clouds, if these point clouds are sufficiently dense, works reasonably well. In terms of the synthesis, so if it's some canonical object, such as a human body, I don't think that it's unreasonable to assume that the topology is fixed. If it's something else, if it's some arbitrary class of shapes, then of course it is a more challenging problem how to generate meaningful mesh that has, for example, that has manifoldness, and maybe it is closed, watertight, and so on. And these are basically some global constraints and local constraints at the same time that go into the generation. So these are rather challenging problems, generating graphs or generating graphs with some structure. So it's not only generating the embedding coordinates of the nodes, but also the topology itself. I think this is far from being solved yet. I think, well, you had a paper on this topic with Matthias, if I'm not mistaken. Max recently had a paper on this, and probably a few other papers. Yeah.
Yeah, I think this is definitely a far from solved problem. I think, well, Max, also feel free to chime in. I think we can ask a few of these questions from YouTube. So one question, I guess, so how fast can these graph-based methods run, especially when finding 3D correspondences? Can we make them run in real time?
Right. So, I think the example that I showed, basically the implementation on a smartphone, it is very fast. It's more than 200 frames per second. So I think this answers that, of course, with some engineering, it can be done. It can be done very efficiently.
Yeah. Yeah. Hello. May I ask a question, Angela?
Go for it. Just feel free to interrupt and chime in.
Yeah. Yeah. Thanks for this very nice presentation, Michael. I really enjoyed it. I have a question about, you pointed at open challenges, which is generating graphs, especially of different topologies. Do you think there, like an implicit representation, at least for 3D shape generation, is more suitable? Or do you see that it will be possible to generate different topologies? Or even, like, you know, have a dynamic graph that changes topology and things like that?
Right. So I think, well, this is an excellent question, and I think it probably has to do more with this idea of working across representations, because depending on what kind of properties you care about in your problem and you want to preserve, and depending on what kind of data you're working on with, there might be a gap between what is the native representation you want to use to guarantee some invariance or some conservation, versus what is convenient to work with, because that's your input. And implicit representations indeed are a very powerful way of representing geometric objects. So they have, well, obviously their advantages and disadvantages. So I've seen a few works. I think one of them was a recent paper from the group of Pascal Fouat at the PFL, where they combined meshes with implicit representations. But again, this is something that probably very far from having the last word in this field.
Maybe, hi, Michael. Maybe I can ask just a couple of questions. So first of all, thanks for a wonderful talk. It's kind of amazing how much you managed to pack in. But I have a couple of questions, and I mean, I guess my questions are more just an invitation for reflection rather than an actual question. So one of them, I think you mentioned briefly, but has to do with the amount of training data that we have. And basically, you know, the story in computer vision typically is that we have this massive amount of training data. And of course, with 3D deep learning, we are getting more and more, but we're still nowhere near the scale that you know, the initial breakthroughs happened in standard computer vision. And I guess my question is, like, we already have some, you know, kind of impressive results, but do you have a sense of how much data is necessary? And also, I myself have been surprised to some extent how little training data sometimes can be sufficient to get some interesting results. So do you have maybe some thoughts about that?
Yeah, I think this is a very good point. And so if you think this is not only a problem in geometric deep learning, I think this is a problem in machine learning in general. So the question of basically how much assumptions do you put into your model, basically the inductive bias. If the inductive bias is stronger, it obviously restricts and reduces the number of degrees of freedom, right? And the expressive power, of course, of the system, but it allows to use less data. So probably in images, it's a good example. If you use just standard multi-layer perceptrons, you will need probably a humongous amount of data, and it will never really work because of the curse of dimensionality in these high dimensional spaces. If you, for example, think also of, let's say, if you have objects that undergo rotations, so convolutional neural networks are also extremely unsuccessful with dealing with such cases. So you need also a lot of data and a lot of maybe synthetically augmented, but if you just make rotation invariant convolutional neural networks, you don't need all these data augmentation. So in some cases, the data can be synthesized, so it's not an issue, right? So you take just, I don't know, images from ImageNet and you rotate them randomly and you train your neural network. But it's a pity to use just brute force when you have clear ways of incorporating these inductive biases if they make sense. So in case of shapes, for example, what we've seen in our works on correspondence, that we could use really a tiny amount of data in the order of hundreds of shapes. Well, of course, we are talking about correspondence between points, so it was probably in the range of hundreds of thousands, but still it is a far cry, orders of magnitude less than what is used in computer vision. So I think probably my short answer to your question is that right inductive biases save you from having a humongous amount of data.
Yeah. Maybe I can also add to, I have some thoughts about this also. So I think for problems where you only need to look at that locally, right? So for example, like for shape completion, like you don't need so much data because like every local region is one training data point. For problems where you need to reason about the full shape, then I think you need much more data. And that's why sometimes it's surprising how well it works, because like basically every local patch is it's a training data point, and if you add up over your 400 scans, maybe you end up with millions of points.
I totally agree. I think, well, there is probably a little bit deeper aspect to this. So first of all, I completely agree. And this is exactly what we've seen also in correspondence problems, that if you look locally at shapes, they are rather poor. So, well, what's the number of geometric structures that you can see in a small patch? Now, of course, then the question is how to combine them together. So the questions of structured output, for example, we did it, and Max in his work as well did it with functional maps. There are probably other ways of doing it. So somehow you basically make global sense out of these small patches. I should say that basically this relates to the question of compositionality, right? So we know that why we like deep learning architectures, in particular in convolutional neural networks, that you can build complex features out of simple ones. And basically, the first architectures or the early architectures, such as AlexNet, were shallow with big filters. They were gradually replaced with very deep architectures with small filters. Now, at least for graphs, this doesn't work. So in graphs, there are some structures that you cannot compute, you cannot represent no matter how deep you go. So even such a banality as counting triangles is impossible with this message pass in neural networks. I'm not sure that this has been at all addressed in geometry, in meshes. Probably meshes are much more optimistic compared to graphs. You might have at least some form of compositionality there.
Maybe I ask just a small follow-up question, which I feel is related. And you know, you kind of have, like in your talk, you touched upon two different approaches, and sometimes they're, as you mentioned, maybe even designated incorrectly, which is this difference between invariance and equivariance. And kind of in your experience, because I guess equivariance typically is a little bit more expensive than invariance. You know, you need to keep track of the signals, and even, you know, implementation wise, it's not trivial, and sometimes you have more weights, but you can maybe express more complex complex filters this way. So in your experience, I mean, would you comment on like when one is more important than the other?
Yeah, well, it's an excellent question. So maybe I was not vigorous enough distinguishing between these two things. So convolutional neural networks, basically they have two building blocks, right? So they have convolutional filters and pooling. And the idea is that your convolutional layers are equivariant. So basically they commute with shift. And if you attach multiple layers, well, non-linearities are pointwise, so they don't break the equivariance. And you have basically the collection of convolutional layers is overall equivariant if it's even multiple layers. Then you do pooling, and pooling gives you at least approximate invariance. Now, same thing has been applied to graphs as well. And in meshes, so if, for example, you have rotation ambiguity, there are several ways of dealing with it. You can do it, for example, with just keeping all the possible rotations of the filter. You can basically do angular max pooling as we did. And we didn't really see much change in performance. We also compared, for example, for keeping some canonical orientation. I know that Taco Cohen argues against it in his paper on gauge equivariant neural networks. I have not seen a convincing argument that shows actually experimentally that one is better than another. I think, and that's exactly where my last comment of trade-off between theory and performance. At the end, these cool general mathematical concepts, when they meet reality, they look like let's say the heuristics that we've done, and they work more or less the same.
Okay, great. Thank you.
Maybe going back to something that was a little bit touched upon earlier, also in your open questions here about incorporating this like global structure topology. And so what do you think? I think a lot of successful kind of generative approaches in various kind of domains often go from like a coarse defined structure, and usually in like an image domain or voxels or something, there's a natural downsampling, upsampling already defined based on the representation. Like, what do you think about like, do we need to have that kind of structure here when understanding graphs and meshes? And what is the right kind of primitive or downsampling approach when we're taking a look at this kind of representation?
Right, so I think this is an excellent question. So in fact, I said in the beginning that I'm keeping completely unaddressed the question of pooling or the analogy of pooling. So in graphs or in meshes, the analogy of pooling is coarsening. And if an image is, there is more or less one way to do it, right? Basically, you just subsample your grid. In graphs, there is a zillion of different ways you can do it. And therefore, something that doesn't have a complete analogy, let's say in traditional CNNs and images, is, for example, learnable pooling. So in graphs, you can do a pooling operation that is optimized for the downstream tasks. So there have been several works in graph neural networks with differentiable pooling, such as work of from the group of Yuri Leskovets and several follow-up works. In meshes, in principle, you can do it as well. I think most people just do coarsening and some upsampling, especially when the topology of the mesh is fixed, like in our synthesis applications of human body parts. You can just do it once. So you create a hierarchy of meshes, coarsening, and then and basically the coarsening and the upsampling operators on these meshes to transfer the features from the coarse to fine nodes and vice versa. And you stick to it throughout your architecture. This is what we've done. We've done at least. Whether you can optimize it as part of the pipeline, probably yes. I don't see a simple way to do it.
I guess I think there have recently been a couple of sort of hybrid approaches to first generate, when the topology is of course not known, to try to generate the topology first and then apply more traditional graph convolutions afterwards. So do you think that's kind of the direction to go, or you think you can generate this fully from like the graph representation?
Yeah, I think so, and it's probably deeper. So for graphs, basically, this kind of so I call this latent graph learning, right? So we somehow in graph neural networks or in geometric deep learning, we come from the assumption that the underlying domain is given. So you're given a graph, and you just need to learn some filters of this graph. But in many other settings, you're not given a graph. So if you think of many problems, let's say in biology, so these networks, like protein-to-protein interaction networks, are not given. So they come from experiments that are expensive, they are noisy, they're incomplete, and you really don't have the graph, or maybe you have some coarse idea of what this graph might look like. And learning the graph together with the filter sometimes might be more important than the downstream task. So we had a recent paper where we looked at, well, it's not related to 3D geometry, so it's still deep learning on graphs, where we looked at electronic health records of patients, and we tried to build networks of patients that allow the best diagnosis. So basically we had demographic features of the patients and imaging features coming from brain fMRI scans. And we try to predict labels such as age or whether the patient has Alzheimer's disease. So the good thing about this, that in these cases, you don't really know what the graph is. So you know that there is some structure, some intrinsically low dimensional structure that underlies your data. You have no idea what it is. And that's why I mentioned why it is related to manifold learning. That was exactly the premise of nonlinear dimensionality reduction, where you assume that your data lives in very high dimension, but it can be explained by a small number of degrees of freedom. So it has some intrinsic low dimension. And these methods, basically the blueprint for manifold learning was construct some local representation of this structure, basically k-nearest neighbor graph in most cases, embed it into low dimensional space by preserving something. So let's say in isomap, that was using multidimensional scaling, trying to preserve geodesic distances on the graph, and then do some machine learning on it. So why these methods were really didn't go way beyond, let's say, data visualization, that usually this kind of low dimensional structure doesn't emerge in the native representation. So you need to do some massage of the data to extract some features, which in the handcrafted world was difficult. Then the construction of the graph was completely decoupled from the downstream task. So you have to tune a lot the parameters of what's the number of nearest neighbors, what's the radius of basically how you construct the graph. So graph neural networks allow to package all the stages of this construction into a single end-to-end differentiable pipeline. So you can construct the graph and filters on the graph and basically the downstream task in the same pipeline. And basically taking these two meshes, there is more stuff to meshes, right? Because it's not just graphs, so it's not k-nearest neighbor graph. You need, for example, to ensure that there are discrete manifolds in some settings. So you need to incorporate some priors about how this mesh looks like. And there are many important problems where these rules of how the graph should look like are even more restrictive. So in knowledge graphs, for example, knowledge completion in molecules. So molecules are not just any graphs. They have very clear chemical and physical rules of how these graphs are constructed. So they're actually constructed from some smaller substructures. You can probably use this analogy for shapes as well. I think Leif Kobelt set a work in that direction, basically building shapes from some small primitives. So this is something that has been done in molecular graphs for something like 3 years.
I have one other question. So do you think for problems like reconstruction and completion, this invariance to isometric deformations is desirable? Or you think that then the filters should be sensitive to different deformations?
Good question. So it's
maybe another related question, which is almost very related. So once you know a specific object, let's say humans or faces, does sharing weights make sense, or it would make sense to have also like basically filters that depend on which part of the object you are, given that you know this topology ahead of time?
Yeah, of course. So probably it very much depends on the problem, right? So even with human shapes, so if you want, for example, to do correspondence between faces, you want to be as agnostic as possible to the different to the variations of the faces, right? So no matter if you have a large nose or a small nose or wide eyes or narrow eyes, you still want to say that these are eyes and correspond them accordingly. If it's a face recognition problem, for example, you really want to nail down these very minute differences of somebody having a slightly bigger nose or slightly wider eyes. And these are the opposite of each other. Now, most of the architectures, so they can combine both and actually learn what makes sense for the specific task. If you take, for example, dynamic graph CNNs, they are both local and global, right? So if you look at the way that this edge conversion is constructed, it's actually explicitly global. Maybe let me try to go back to the slide where I show it. So we actually made it dependent on the coordinate of the specific vertex and the difference between the vertex and the neighboring vertex. So that basically that was an extra hint, and you can call it also an inductive bias that helped significantly to learn. So yeah, basically short answer to your question. So this construction here, actually in the actual implementation, we made the second argument the difference between xj and xi. So you have a function that depends on the position of each point. So as a particular case, you can get point net, right, which depends only on xi, and it's a shared function. There is no aggregation. Or it can depend only on the difference between xi and xj, and then you get back to something similar to Laplacian-based isotropic filters. But in the most general case, it depends on both.
Makes sense. So maybe I have another question. So, like often is the case that we, for reconstruction problems, we try graph neural networks, and we end up having less details than using, for example, like mapping the shape into a 2D image, for example, with displacement maps, and then doing convolutions. We end up having less detail. So what do you think is lacking? So is it the lack of rotation, like that lack of orientation? Is it the difficulty that you have different resolutions, different meshing? What is the key thing that is lacking that graph neural networks don't achieve this performance that convolutional neural networks achieve?
Well, I'm not sure that lack of details there is really something that is somehow intrinsically problematic with these approaches. So probably a good way to think of it is having some maybe core structure, and then you can think of it as extra texture on top of it, geometric texture,
right?
That contains the details. I should say that I have not seen works or many works that try to do to intrinsically handle the texture correctly. So that could probably be one of the next open questions. I should probably have mentioned it, dealing with textured shapes, where by texture I mean not just per vertex or per face values, but something more similar to UV coordinates, where you have texture mapping, where the texture can be in much higher resolution than the mesh. And that could be a good trade-off, that you still work at least approximately coarsely intrinsically on the mesh, but you also have a lot of details that come from your texture that you want to handle properly.
I guess finding the map, right? So finding like the UV map for general shapes would be also very challenging, because. But
you don't. So I think this also relates to your previous observation. It doesn't need to be global. I think most of the UV maps are constructed globally. Here it can be local. So you don't really need to stitch it together. It's, once you construct this representation, you just store it somehow per page, let's say.
I think we're just about out of time now. If there's one more question, maybe. So I'm kind of curious about this textured mesh kind of direction, because that seems like a pretty strong advantage to using this mesh kind of representation, is to be able to incorporate these different data modalities and also at different resolutions. In terms of like the color representation, maybe we can also get the same kind of power that we get from the 2D image understanding, because it at some point is pretty close at this point to a textured mesh representation, where it's being mapped to this kind of image domain, although the image itself will be distorted in the UV kind of patch. And like, do you think we need to develop like new tools to combine these kind of like features together?
Good question. So I'm not sure these are new tools. It's probably retooling the existing tools. So if you think of, let's say, even global parameterization, right? So at least for certain for Geno-zero objects, we can uniformly by uniformization theorem we can conformally map them to the plane or to the sphere, right? So basically, they are convolution because at least locally you have angle preserving transformation. So the only ambiguity is the scale. So you just have the filter that is oriented canonically. You just need to change its scale. So you can, in principle, apply a standard CNN in that space, so adapting the scale of the filter based on the conformal factor. So this is obviously an extreme example, and usually these maps are very irregular in the sense that the conformal factor can the dynamic range can be orders of magnitude. So it's not necessarily the right way of doing it, but just an example. I think usually in these kind of architectures, in mesh architectures, we don't really consider any information that lives, let's say, on a face or on a triangle. We just consider the nodes and maybe the edges. Basically, adding this extra structure is important, and I have not seen it addressed. On graphs, actually, there are models, what is called quantum graphs, not related at all to quantum mechanics. It's basically graphs where edges are considered as one-dimensional intervals. And for example, you have diffusion that is propagates along an edge, so it's not an immediate interaction between two nodes. So something similar can be done for shapes as well, but they're two-dimensional.
Yeah. I think there's one interesting question on YouTube, and then I guess we can wrap things up that just came up. So could you briefly discuss the possibilities and issues regarding pre-training graph neural networks, for instance, on proteins in an unsupervised fashion?
Yeah, good question. So for some problems, this is very natural. So if you think of graphs, for example, like social networks, you can do one of the standard ways of pre-training is edge prediction. So you have a graph, you remove one of the edges and you try to predict whether there is an edge or not. Usually it's done in the form of node embeddings. So you compute some representation of each node, and then, for example, you want let's say the inner product between the node embeddings to be proportional or associated with the probability of having an edge between them. So for shapes, it's a good question. What would be the self-supervised setting? I would guess something similar to what is done in text. So some kind of fill the blanks. So for proteins, for example, one possibility would be is to predict the amino acids and that underlie that part of the interface. So one of the ways, for example, what can be done is you mutate the side chains of the amino acids. So amino acids have some basic component, and then the side chain is different. We have 20 proteinogenic amino acids in our body. So mutating everything to alanine, which is the simplest amino acid, and trying to predict from somehow the context what was the original amino acid. So that could be one way of doing self-supervised learning that we've been experimenting with. It's still far from having a definite answer, but that's the first thing that comes to my mind in the context of proteins.
Cool. Yeah, that's, I think, still big open questions in a lot of areas in terms of less supervision. So I think it's about time. So thank you again, Michael, for the great talk and a lot of interesting insights regarding like graphs and meshes, and also to Gerard and Max for helping with the panel.
Thank you, guys.
Thank you, Michael, for the talk, and thank you, Angela, for organizing. Yeah, bye-bye.